This is a course about statistics. I'm sure you've seen statistics before. I'm sure you've seen them in the newspaper, seen them on television. Just about every issue that's discussed these days is usually backed up with arguments that are supported by statistics. Often these statistics are just presented as descriptive ones. They help you describe a pattern that might exist in percentages or averages. Statistics is much bigger than this. Statistics is a way of not only describing patterns and defining general trends using numbers, but statistics also applies inferences based upon probability. And basically what statistics boils down to is describing a pattern in some form, and there are a multitude of forms for describing the patterns, and then to look at those patterns and make a decision. Did that pattern occur by chance, or is that by design? And the second part involves assigning a probability to the existence of that pattern. If that pattern just occurred by random chance factors, or is that some sort of design feature? Is it some sort of consistent contrast between two states, contrast between two variables? Is it something that really exists in the environment as a feature of it and not something that just occurred by chance? That's the added advantage of doing statistics. It makes you reason better by assigning probabilities to your decisions. And people are very good at making decisions without assigning probabilities. Most of the decisions that we make, usually we do not explicitly assign a probability to them. However, all of them could have a probability assigned to them, and you can actually calibrate how likely it is that a certain decision is going to lead to a certain result. And when you're predicting things like your retirement fund and your stock investments, or whether your real estate investment, when you buy a house, whether that's going to go up or down, all those can be itemized and a probability assigned to them, just like you see probabilities assigned to things, when you play cards and you play gambling games, you see probabilities assigned to those. Probabilities can be assigned to any kind of decision. And what statistics allows you to do is itemize a pattern, describe something in the environment clearly with numbers and with measurement, and then decide, using probability judgments, whether that pattern could exist by chance or it exists by some kind of design. And when you're doing a study that involves treatment, say an outcome study, say for treatment for an illness using a drug, and you give people the drug and you give some people don't get the drug, you will see a pattern, and the pattern could show a difference between the two groups, but that might not be enough. You have to find out or discover, you have to figure out if the likelihood that pattern, that difference could have occurred by chance, and then make a decision. Either that it did occur by chance, or that it's so unusual, it's so unlikely to have occurred by chance, it must be because of the manipulation of the drug. It must be something that you did. It must be a pattern that exists by design. So statistics in general allows us to think better. It allows us to think in a more logical fashion, in a more deductive way, and it allows us to avoid errors because we're guessing, because we're making decisions and choices based upon intuition or hunches and things like that. Statistics gives you a probability associated with your decision, and from that you can make better decisions, you can think more clearly, think more logically. Statistics, the development of it in the 20th century was a major advance in the investigation using science generally. The logic of it is kind of interesting because it is not deductive. It is not something, you can't use statistics to prove anything. Statistics is used to describe patterns that exist in numbers and to figure out whether those patterns could have occurred by chance or not. And there's a multitude of different ways of doing that, a multitude of different ways of defining a pattern, a multitude of different ways of contrasting, so that you can actually get an index or indices representing the patterns, and then make decisions about whether the patterns could exist by chance or not. Well, the first stage in this is recognizing what we're doing with statistics, the kind of reasoning we're involved in. And here I have on this slide two major styles of reasoning, two major aspects of logic. The first is deduction, and deduction is the classic method of logic is the method of logic used to prove things. And here's a simple syllogism, which is a simple deduction. All animals with stripes are zebras. That animal has stripes, so that animal must be a zebra. And you can see here a logical juxtaposition of category descriptions and a logical deduction from those descriptions to a conclusion. Now, statistics doesn't allow us to make deductions. We can't prove these things. What we're going to do with statistics is make an induction. And inductions represent a reasoning under uncertainty. They represent partial reasoning. They're almost a kind of logical error in a sense, or the error. The only difference we're going to incorporate in statistics is the error is going to be quantified. So the uncertainty I have in my judgment is going to be made very explicit. Whereas most of the time we make judgments like this, inductions like this, and we don't make our error explicit. We make them as if they're deductions. So here's an induction. Since most animals with stripes are zebras, that animal with stripes is a zebra. Now here I've got a pattern that I've induced from a sampling of zebras, and since I've sampled them and discovered that all the ones that I sampled actually have stripes, I'm going to conclude that any other striped animal I see must therefore be a zebra. Now because I haven't actually examined every zebra, there might be some without stripes. I'm going to make an induction. There's going to be some uncertainty, some error in my judgment. And that error I will quantify using statistics. So statistical inferences are inductions in which generalizations are made from samples, and the error in the generalization is quantified. So that even though you make an induction, you could always be wrong, the probability that you're wrong, the probability that you're incorrect is always apparent. It's always quantified. It's exactly there in the statistics that were conducted. Now this is contrasted with how people usually reason, in which they make inductions. We make them all the time, and we never quantify how uncertain we are. And most of the time people actually make inductions as if they are 100% certain. So we'll draw conclusions under uncertainty when we don't know everything that we need to know. That's actually a particular strength of human reasoning in a certain sense, because it enabled us to always make decisions. So when we're out in the environment and we're out trying to figure out what to do, we don't get stuck. We don't get immobilized by the fact that we don't have all the information that we would need to make a deduction. We take what information we have, we make a decision. What statistics allows you to do is quantify how uncertain you are, so that if you make inductions like this, you'll know how far off you may be, and it's always contained in the statistics that the conclusion could be incorrect, and the probability of that. So what statistics gives you is a kind of strong induction. It gives you a kind of quantified or empirical induction, and that's much better than using guesses and inductions without that. Okay, well, this is part of general human reasoning, and psychologists have studied this. Psychologists have put a lot of research into how humans reason under uncertainty, and one of the things that they do is they use heuristics. They use rules of thumb, and they use approximations. And they tend to formalize these. And although many times the heuristics are not even known to the person, while they're making decisions, and only by asking people later, how did you decide, to buy that car over there? How do you decide, which school to go to? And from analyzing how people respond, you can figure out what kind of heuristics they used. Well, the three major heuristics are anchoring, representativeness, and availability. Availability has to do with reasoning concerning how available information is about the decision in our memories. So if your brother just bought a car last week and he told you all about it, and you went with him and helped him and everything, you're going to know a lot more about buying a car than if you didn't have that experience. However, that experience is going to flavor with decisions you make about buying your own car. So the experiences that you had in your memory about that experience are going to influence your future decisions, and if it was a positive experience or a negative experience and so on. If there were certain facts about financing cars that you learned in that experience, they may influence your decisions to buy your own car, or future decisions about buying about car buying. Representativeness is a very common heuristic that involves matching characteristics of stereotypes, essentially, or prototypes, with new examples that may or may not be part of the stereotype. So if I'm going to make a decision about hiring someone, and I'm going to hire an accountant, and I have a lot of ideas about accountants already, what they're like and what kind of skills they need to have and what their personality is like and things like that. And I meet job applicants, I'm going to try to match the job applicants, my perception of what the skills they have and what their characteristics are, to the stereotype I have of what an accountant ought to be, or what the person ought to have who's filling that job. Well, I go about interviewing people and making all these matches, and I use representativeness heuristic in order to do that. And I may actually make lots of mistakes, but in general, I'll be matching, on average, characteristics that probably match the requirements of the job I need. Unfortunately, we never really learn, from those kinds of heuristic applications, when we make mistakes. I guess the job applicant, certainly your car, you might discover that stereotypes or availability information you were using to make a decision was leading to a bad choice. But most of the time, we don't really get feedback about our decisions, or we don't get enough information about the decision we made in order to change our stereotypes or change our heuristics, and we keep plodding on with the same ones most of the time. The final one is anchoring, and we're going to do a little exercise here to illustrate what anchoring is. Anchoring is a dominant heuristic in the application of statistics. All of the others are used as well. And anchoring is an easy one to demonstrate. Anchoring is an easy heuristic to show that everybody has it and reasons by it. And that's going to be, we're going to reason about Einstein's IQ and think about that. And then I'm going to give you some information about IQ, and we'll see how that information might anchor your judgments. And finally, on this slide, I have a great quote by Mark Twain, who once said that there are lies, damn lies, and statistics. And I'm sure he's referring to the usual manipulation, or the common manipulation of statistics by just about everybody to make their case. And certainly you can manipulate the descriptions of patterns, and it's hard to manipulate the application of probability, but most of the time when people are manipulating statistics, they don't get to that point. But if you really know statistics, if you really understand them, you can see your way through manipulations. You can see your way through incorrect calculations or mischaracterizations of numbers, mischaracterizations of averages or percentages of things like that. And you can also recognize that most of those statistics that are presented in that way are not usually presented in a probability framework, and that makes for all the difference in their accuracy. Here we have an example of one of the heuristics that I mentioned before. This is the one of anchoring. Anchoring occurs when numbers that you have in your memory or numbers that you've heard recently influence current judgments about those same numbers. Decisions about numbers that are influenced by recent numbers or estimates you've heard before, or estimates that you have in your memory about the same conditions. And we're going to have an example here. Here's Albert Einstein on the cover of Time magazine. Albert Einstein is obviously a very intelligent person, and he's famous for theories of relativity, for quantum physics, and of course his famous E equals mc squared equation expressing the relationship between mass and energy. And the atomic bomb is sort of the fruition of his work. And I think a lot of people identify with him because he was instrumental in getting quantum physics going, and the atomic bomb is such a dramatic, great manifestation of modern physics that we identify him with that, even though he was not actually an atomic bomb developer. At any rate, we revere him as being a very, very intelligent person. And what we're going to do now is estimate what is the magnitude of his IQ. How big do you really think it is? You probably heard about IQ numbers from TV shows, movies. Sometimes say what their IQ is, or somebody will estimate someone else's IQ. And there's sometimes they have a little contest about, who has the higher IQ. Well, what I want you to do now is think about, what do you think his IQ actually was? Albert Einstein, intelligent person. What do you think his IQ really was? And estimate a number. Estimate a number in your head. I won't give any numbers as examples because they'll start to anchor you. So think about a number and from whatever you know about IQ, and just keep that in your head. Okay, so now you've got your IQ estimate from the slide before about Einstein's IQ. And you probably made that estimate from knowledge about IQ that comes from, TV shows or movies in which IQ is presented. Maybe you took an IQ test before, you have a better sense of the numbers. But sometimes numbers are presented that are way outside the ranges, like 700 or 800 or so for somebody's IQ. Well, here's some basic facts about IQ. First of all, the average IQ score is set at 100. So the score is actually calibrated, so it's set, the middle part of the distribution is set as 100. IQ scores above 120 are uncommon, and IQ scores above 130 are very rare. So somebody to have an IQ score, say, of 140 or 150 is extremely unusual. And I think the common depictions of IQ, often based upon that, people often make much higher estimates than what these numbers would convey. And that's the point of this, so that once you know about IQ numbers, those numbers tend to anchor you. So once I've told you that an average IQ is 100, no reasonable person is going to say, well, Einstein's IQ, even though he's obviously a very intelligent person, is going to be a score of 700, because a score of 700 is impossible to get. Even if you answered every question on the IQ test correctly, you still wouldn't get a score in that range. It's not calibrated that way. So now that I've told you about IQ, these numbers that I've relayed to you ought to be anchors now for a new judgment. Based upon the idea that the average is 100 and so on, you should now give an estimate of IQ for Einstein that should be, clearly not more than 150, and probably in the range of 140 or so. And that's how anchoring works. You have memories of numbers and how they're supposed to be set in your head. You have a sense for expectations about what numbers are supposed to be in the future. And you make predictions or estimates of future numbers, and those future estimates are anchors. Sometimes when I do this in classrooms, I'll ask them to tell me out what their IQ estimates are, and often the first people that make a response, they give me a number, of 500 or something, and that serves then as an anchor for the other people in the class. So once they hear that 500, they tend to use that 500 and base their judgments, either agreeing with 500 or saying that it should be higher or lower. But the 500 now becomes an anchor. So when you're dealing with decisions under uncertainty, you tend to find numbers that you're used to hearing or estimates based upon essentially a representation of numbers that you have as sort of a model for how those numbers ought to be scaled and how they should be related to each other. So now that you know about IQ, you should be able to make a much better informed estimate of what Einstein's IQ likely would be. And I don't know if Einstein ever took an IQ test. People talk about his IQ all the time, but I don't believe he ever took one. And I don't believe his IQ number was ever actually calculated. Now what statistics does is statistics essentially unanchors you from preconceptions about numbers. So when you think that income ranges are in a certain number range, or a distribution of scores ought to have a certain mean, or males are different than females by a certain magnitude, you're basically expressing a heuristic involving anchoring about those numbers. When you actually go out and do a study and collect data, collect numbers, and scale things appropriately, you get the facts about that situation. You're not anchored by preconceived ideas that are in your memory. The numbers you collect in your study are the numbers, and the statistics that are calculated is the pattern in that number set. And preconceived ideas you have about score ranges and so on are now dispelled by statistics, by these facts of numbers. And statistics tends to de-anchor people in that it stops them from using heuristic reasoning and makes it, or at least makes the heuristic reasoning much more based on facts about the numbers, on their true ranges, and not anchors that are in memory. Statistics textbooks often divide statistical procedures into two main categories: descriptive statistics and inferential statistics. Descriptive statistics are those that are used to describe a distribution, show trends that are in the means and the variance of the distribution. And they were developed early in the history of statistics, and for many years they represented a novel approach to analyzing data. I mean, the fact of data itself having to empiricize variables was something that was novel at one point, and quite a revolutionary idea in terms of analyzing patterns. The next major development was inferential type statistics, in which the patterns were analyzed for their probabilities. So experimenters would design a study in which they controlled variables and assigned subjects to certain conditions. Then when they compared the subjects, compared their means, for example, the groups and things like that, they needed statistics that were going to assign a probability to the distribution differences and test hypotheses about differences. And that caused the development of inferential type statistics. This distinction is really one more that's historical than anything else. It's something that does roughly dichotomize statistical procedures, but there is some overlap across these two categories. For example, the correlation coefficient is also used to make inferences, and it's a little misleading to keep it up there with the descriptive statistics. The distinction I make between statistics procedures is you have procedures that are designed to illustrate and depict a pattern, and then you have procedures that are used to make inferences about the pattern, and those inferences are all probability judgments, and that's the distinction that I make between statistical procedures. Again, this is mostly historical. This doesn't really have a bearing on how you use the statistics so much, and they're a little misleading. They cause people to think of statistical procedures as being either one or the other, when actually they combine both things. Statistics are used to examine all sorts of questions these days, and here we have three examples. We have the ratings of the Nielsen families to decide which kind of shows they're canceled and which ones are not. If a business advertises on the television, they get lots of information, lots of statistical analysis of who's watching their TV shows, what their ages are, their gender, all kinds of demographic information. And television stations will target shows for certain demographics of people that are watching at certain times of the day. Well, they can't do that without statistics, and lots of data is collected that examines that kind of question, or that set of questions. Do SAT scores predict how you'll do in college? That's a very interesting question. Everybody took SAT scores presumably to get into college, and the relationships between SAT scores and college performance are examined using statistics. And decisions are made about people getting in college based upon SAT scores and their presumed relationship to how well they'll do. And finally, we have polling, or when we have elections and have data collected at our polling stations. Essentially what you're doing is expressing your opinion about a certain candidate. And polling data is very statistics intensive. So we hear lots of information about margins of error, not only just the outcome of the election, but we get information about how accurate it was. And when elections are close, like we've had recently, errors and unreliability in polling is something that we notice. If an election isn't close, no one takes the time to go examine all the inaccurate or all the polling problems that may have been there. But when the election is close, those are followed very closely, and we learn about all these errors and difficulty that people have actually just collecting votes. You also hear about exit polls from voting places and the inferences that are drawn from those. All that's done through statistics. And of course, one of the most interesting applications of statistics in this area is when elections are predicted with only a certain amount of data in place. How do statisticians do that? How do they figure out that a certain candidate has won when only maybe 10% of the polling is completed? All that involves inferential statistics and answering statistical questions. Well, here are one of the statistical questions presented in a little more detail, and there might be something that's quite relevant for you. And that is whether SAT scores predict college success or not. SAT scores were developed as an aptitude measurement that would allow admissions departments in colleges to pick people based upon a sort of common denominator, a sort of common element that would predict success in college that wasn't dependent on things like high school grades or what kind of program you went to, whether it was rigorous or not, or had a reputation of certain rigor or not. It represented a kind of common test, the idea that you would advance people based upon their merit and not based upon their idiosyncratic things that were hard to quantify or clearly relate to an objective standard of merit. And the SAT score, the system really needed to make everyone's academic performance scaled in a similar way. So the decisions would be based on an objective standard and not something that was subjective or something that was just unclear in its relationship to college performance. The problem is, while the question is a classic statistics problem, it's one in which you're calibrating statistical predictive power. That's done with correlational techniques and with regression models, which we'll learn about later in the course. But statistics is applied to this. It's essentially a very statistics-intensive kind of question. So you collect SAT scores, you collect things like college grades or other measures of performance in college, and you correlate these things. If there's a relationship, then it does provide support for using the instrument to make selections. If the relationship, though, has to be of a certain magnitude, you can't just have a low relationship and then use the test this way. You want something that's got at least a moderate to high relationship with the criterion measures, the things you're trying to predict. Well, here's a statement from the College Board. And the College Board is obviously invested in people using the test to make selections. There's also a financial interest that the Educational Testing Service has in developing these tests and people paying money to take them and to use them. They want colleges to use them from that interest. Well, here you see a description that's in text form. So they're describing the relationship between the two things just in text. There's no numbers. So there's no indexing here of the relationship. It's all described in text. Now, that's either done because you want to try to convey things in a simplified form so that the reader can understand this, or you actually might be trying to obscure the fact that there might be low relationships with language that clarifies the relationship or describes the relationship in much more rosier terms. And I believe that's what the College Board has done here. You see, for example, the first sentences. The SAT has proven to be an important predictor of success in college. Now, already the word important is in there as suggesting that the relationship is relatively high. Its validity as a predictor of success has been demonstrated through hundreds of validity studies. These validity studies consistently find that high school grades and SAT scores together are substantial and significant predictors of achievement in college. So I think the language is actually more supportive of the SAT than it should be, because we're going to see another slide here from a group called Fair Test, in which they actually present numbers. And if you know anything about statistics and how these prediction problems are set up, the numbers are relatively small. They're not really that important. The problem is most people don't know enough about statistics to make a judgment about it or express an opinion about it. And because the social need for the test is so high, there's a tendency to gloss over weaknesses of a test because we need it. We want it. We want to make decisions based upon a test in something that seems objective rather than something that seems subjective. Here's the characterization of the relationship from Fair Test, which is an organization that's sort of a check on test development and kind of a counterpoint to the advocacy for tests and their widespread use in the United States. They present another description. Notice this description, though, does have some numbers in it. They're trying to convey the scaling of the relationship between SAT scores and college grade point average. But they're also sort of falling back on text description. I think here Fair Test is trying to simplify and characterize findings, but they do add a few numbers in their percentages, and notice that they're not anything more sophisticated than that. And this summary is really one for an audience that's not statistically savvy and probably would not know what the indices from correlation and regression actually mean. And I also wonder if their characterization isn't too negative, but you can make your own judgment. Their statement, their first line is, validity research at individual institutions illustrates the weak probability of the SAT. Now notice that the College Board said that the SAT has proven to be an important predictor of success in college. Then they go on to characterize some of the results. The one study looked at the power of high school class rank, SAT 1 and SAT 2, in predicting cumulative college GPAs. Researchers found that the SAT 1 was by far the weakest predictor, explaining only 4% of the variation in college grades, while SAT 2 scores accounted for 6.8%. By far the most useful tool proved to be class rank, which predicted 9.3% of the changes in cumulative GPAs. Combining SAT 1 scores and class rank inched this figure up to 11%, leaving almost 90% of the variation in grades unexplained. Now that's a very important point, that even though SAT score and even high school rank, class rank in high school, are predictors, they don't account for much variance. And that might not actually mean that much to you, but these are very, very small amounts of variability that these things are accounting for. If you want to make predictions of the stock market based upon this, or whether you're going to buy a house or not, because based upon variables that only predict 4% of the variance, you'd be making bad decisions most of the time. Okay, well, however, this characterization might be too negative. What you really want to see, what you would like to see, are the actual indices from correlation analyses, from regression analyses, and you should know what they are, so you can make your own decision about predictive power. And not take a characterization like this to sway your opinion too much. This is along the lines of the old quote by Mark Twain that there are lies, damn lies, and statistics, and you see the kind of manipulation of the interpretation of scores that comes from people with certain interests in characterizing the scores and the results certain ways. If you become knowledgeable about statistics, you can see through this. You can make your own decision. You can see through whatever way they're being characterized or summarized for you and make your own summary and your own characterization. In the last slide in this section, we're going to actually see some of those numbers, and I'm going to use whatever interpretation skills I have to make sense out of them myself. Okay, finally in this slide, we see correlation coefficients. And the correlation coefficient is an index of relationship. It varies from 0 to 1.0, and it represents a general index of how well two variables are related to each other. Now, this turns out to be a very powerful index for making predictions. If variables are related to each other, then if I have future cases, I can use that relationship to base a prediction. So here we have SAT scores and college success, and this information is broken down to the relationship between the SAT score verbal and math scores with high school GPA predicting freshman grades in college. Okay, one of the problems you have, which none of these studies, well, they probably describe in more detail in the actual paper write-ups, but in these summaries at websites and things, you don't really get all the information. The biggest problem in doing any study of this type is that the freshman grades are not necessarily a good predictor or criterion because people were selected for their freshman class based upon the SAT scores. So presumably only the high end of the range of SAT scores were allowed admission into college, and so therefore the freshman grades of those people are from the higher end of the distribution. Now I think you can intuitively see that, even if you don't understand statistics that well, you can see where that would be a problem. If all I have are the people in the high end of the distribution, my predictive power is going to be lower. Ideally what you would want to do is give everybody the SAT and then admit a random sample of those people into college. And then you can correlate their freshman grades with the SAT scores, because now you get the full range of people admitted, and you don't have a problem with constraining the range of scores, which artificially will push down correlation coefficients. Okay, the next thing that I notice as I go across here, well, just take one at a time here. If they've also broken down this data by males and females, which I don't think is quite that relevant, but we can see if there's any difference. The first relationship is between the SAT verbal and math scores and the freshman grades. You see that all males and females, you have an index of 0.36. For males it's 0.35 and for females it's 0.41. These are roughly the same index for males and females, even though the numbers look different. They're not that far apart. It suggests that the predictive power of SAT is approximately the same for males and females. That 13% there is reflecting the amount of variability in freshman grades that's predicted by the SAT scores. And that's a relatively low number. I think even if you don't know the statistics that well, you can still see, well, gosh, that 87% of the variability in freshman grades isn't predicted by the SAT scores. If it's predicted by anything, it's other factors than the SAT itself. And you can imagine what kind of things predict freshman grades. The next thing you see for HSGPA is the high school GPA. That's predicting at 0.39, which is roughly the same predictive power as the SAT score. The question is the high school GPA measuring something different, sufficiently different than the SAT, that it has its own predictive power, or are those two redundant? Partialing out that redundancy is something that you do with regression, and that's what you see in the third analysis there. That's a correlation coefficient based upon the two combined, and notice that the increase is, it's significant. It's not trivial, but it's actually quite small. And so you see a 1% increase. That's the SAT increment from going from 0.39 for a high school GPA to including the SAT. You only add 1% more predictive power, which is incredibly small. If you were going to base your stock choices based on this, or whether to buy a house based on this, you would be wrong most of the time. So the conclusion from this is that the relationship is relatively small. Colleges should probably not be using the SAT to make predictions, or at least should not be using it as if the correlation and the predictive power is much higher than this. I think if I was doing a study in which I was trying to predict variables and predict outcomes of treatment or something like that, and I got this result, I'd be very disappointed. My results would be essentially interpreted as negative, that the predictive power is actually quite small. It's a marvel, I think, to the demand for a test like this, that we continue to use a test like this to to make predictions, to make decisions, when the predictive power is so small. It suggests to me that we really, really need a test like this. The society, the educational system, they want to advance people, to select people based upon merit, but they see even high school GPA as something that might be manipulated by what kind of high school you went to or what kind of curriculum that you had. And certainly that's a problem. Certainly finding these PAN scores, the score that's going to reflect everyone's ability equally, is a hard thing to find. It would be nice if there was such a test of aptitude. I think my personal opinion is that the SAT test itself is not well designed. When I'm involved in selecting people for graduate school, for example, I noticed that the GRE score, which is the graduate school equivalent to the SAT, isn't measuring things that I particularly use to evaluate whether somebody can be a good student or not. And there are a lot of other things I'd like to know about the student that are not reflected in the score. Things like their writing skill, things like their knowledge of statistics. Things like that aren't measured by the GRE. There's no scale for that. All that we get is a verbal and math aptitude measurement, which is a very abstract thing, and as you can see here, has a very small relationship to the performance measures actually in college. So at any rate, what I'd like to see is a new test, a test of actual academic ability instead of this thing called academic aptitude, something that actually measures what people know that's relevant to being a graduate student generally and a graduate student in psychology, and not these more arcane things that are in these tests that deal with, logical relationships or basic geometry and algebra and things like that probably have some relationship to general performance in college, but they're not the kind of things that we should be selecting people on. We should be selecting people based upon their academic skills and not academic aptitude.